Sun, every second, this hot gas ball releases the amount of energy sufficient for the humanity for 1,000,000 years. Such a colossal volume is released from the core of our star due to thermonuclear fusion, the nuclear reaction that has been happening in the Sun for 5 billion years already.
Thermonuclear fusion is a process in which nuclei of light elements connect to each other with the formation of something heavier. During this, a huge amount of energy is generated.
As early as the beginning of the 20th century, mankind decided to obtain this source of energy and create their sun on Earth. It would seem that it's impossible to reproduce the technology of the luminary. However, scientists managed to do it.
You need to ignite plasma with a temperature of hundreds of thousands of degrees, but it needs to be placed inside a certain non-existing vessel. This vessel is the magnet field. The main idea consists in confining plasma, setting it on fire, and possessing it.
It's been over 60 years since the thermonuclear fusion was first performed on Earth. But why aren't we still getting thermonuclear energy on an industrial scale? What problems prevent scientists from controlling the thermonuclear reaction? Why was it necessary to build the largest thermonuclear installation in the history of mankind to solve these problems? Imagine the future in which you can afford as much warmth and heat as you want. The future where you don't need to buy energy-saving bulbs, turn off all light sources before leaving your apartment, and worry about large bills for electricity. Now imagine there is only one step that separates us from this future. We just need to learn to control thermonuclear fusion, the nuclear reaction that is capable of providing us with an inexhaustible source of energy for thousands of years.
In fact, thermonuclear fusion is an inexhaustible source of energy for mankind, because it's fueled not by some oil or uranium, the reserves of which are limited in the Earth's crust. Instead, it is fueled by deuterium, which is virtually unlimited in the ocean, and by tritium, which the humanity can obtain from other elements that are also sufficient in number. These elements will provide fuel for thermonuclear stations for an enormous number of years.
Deuterium and tritium are isotopes of hydrogen, the first and the lightest chemical element. When heated to a temperature of 90 million degrees Fahrenheit or higher, they will transform into fully ionized plasma. Due to this effect, the nuclei of deuterium and tritium will accelerate so much that they will overcome Coulomb repulsion forces and merge, forming a neutron and a helium core. As a result of each event of such fusion, 17.6 megaelectron volts of energy will be emitted. The prospects of application of thermonuclear fusion are impressive. First of all, deuterium and tritium, which make up its fuel, are completely accessible. Second, the operation of thermonuclear reactors poses a significantly smaller environmental threat than nuclear stations. There is no problem of nuclear waste. But the most important thing is, the energy generated as a result of the fusion is much greater than the energy from any source known to us.
If we compare a thermonuclear reactor and a nuclear one in terms of the energy generated, 1 pound of the source mixture will produce 3 times more energy in the thermonuclear reactor than in the nuclear one. That is, this device would be much more effective if we compare it to other sources of energy production. Following example may be interesting. 3 ounces of the deuterium-tritium mix generate the same amount of energy as combustion of 1,000 tons of coal.
If scientists are aware of all advantages of thermonuclear fusion, why is there still not a single thermonuclear station? It turned out that gaining control over thermonuclear reactions is an extremely complicated task. It took scientists 10 years just to design the first experimental reactor. A special vessel had to be invented and created to confine the incredibly hot plasma. Famous Soviet scientists Andrei Sakharov and Igor Tamm were the first to cope with this task. They suggested the idea of magnetic plasma confinement in 1950. The first experimental installation in the world, known as a tokamak, was built in the Kurchatov Institute. The design of this toroidal chamber with magnetic coils proved to be so successful that a real tokamak boom occurred. As of now, over 300 such reactors have been built around the world. However, neither tokamaks nor other types of reactors managed to solve the main problem, gain complete control over the behavior of plasma. But why did it turn out to be so unruly and unpredictable? What is plasma actually?
Plasma is an ionized gas. It is considered the fourth state of a substance. In addition to liquids, solids, and gases, there is also plasma, a substance that has been heated to an extremely high temperature. Its molecules are falling apart to atoms, and atoms are ionized, and the substance turns into something that is very difficult to keep at rest.
On Earth, in natural conditions, plasma can only be found in the form of electric discharges of a lightning or aurora borealis. In space, on the contrary, it's literally everywhere. The vast majority of matter in the outer space is in the state of plasma. This includes not just all stars, but also the interstellar medium and galactic nebulae. On the one hand, scientists managed to study well the processes that occur in the space plasma. Astrophysics has been engaged in it for quite a long time. On the other hand, it turned out that the accumulated knowledge is insufficient to understand the laws governing the lives of the stars that light up on Earth.
In this case, we create an object for research by ourselves. The physics of the processes is similar to what is happening on the Sun. However, there are inevitable nuances that complicate it all.
Scientists are still not sure about how the particles and heat are exactly transmitted within plasma. How is energy retained in it in the first place? There is no comprehensive scientific theory that would explain all the processes going on in this mysterious substance.
Plasma is indeed a very unpredictable entity. It constantly brings new discoveries and new surprises that can be either positive or negative for us.
Due to the fact that the behavior of plasma cannot currently be controlled by scientists, the release of energy during thermonuclear fusion turns out to be unstable and non-uniform. This leads to a whole string of additional problems. One of the main problems is associated with the destruction of the first reactor wall in the tokamak. Even such material as tungsten, which is the most refractory metal on Earth, cannot withstand the load created by plasma streams.
If during the experiments that we conduct on the T10, the electrons begin to behave in the wrong manner, accelerate, run away, or accidentally come in contact with the tungsten wall, the wall melts in a single second.
Although this event looks very impressive, it inevitably leads to plasma disruption and termination of the thermonuclear reaction. Every such disruption can potentially result in several months of downtime for the tokamak, but in order to receive energy from thermonuclear fusion on an industrial scale, the reactor has to operate in the uninterrupted mode. It's no surprise that the search for the material that would protect the walls from destruction has become one of the most burning tasks that the scientists are facing today.
One of the most promising ways now is to use some light element. Today we use lithium to build a renewable wall. That is, a liquid constantly renewing lithium wall. Such experiments are being conducted all over the world now.
Another problem that emerged very recently and became totally unexpected for scientists is common dust. It turned out that it's accumulated directly inside the vacuum chamber of the tokamak. The larger the reactor, the more dust there is. According to the calculations of the scientists, there may be several hundred pounds in the biggest installations.
Every speck of dust has its own area. It turns out that if there is a lot of dust, this dust is not exactly favorable from the point of view of tokamak, as it absorbs, for example, hydrogen in the form of deuterium and tritium, which is very important for the tokamak. Let's say this dust will absorb tritium, and we won't have enough of it. For example, we observe such problems with the Tora Supra installation. When we tried to achieve an extremely long discharge, it turned out that the gas had gone somewhere. But now it is considered that the gas went into the dust. This dust problem is very serious. It emerged very recently.
Heating and confining high-temperature plasma is still one of the most complicated tasks that science is facing now. Scientists all over the world have been trying to solve this problem for over 65 years. Attempts to solve it include various means and construction of all types of reactors, for example, the Stellarator Wendelstein 7X. The construction of elements of this installation began as early as in 1998. In order to assemble all its essential components, the team of almost 500 scientists worked for 7 years. Also, the construction work is still in progress. The first tests of heating and confinement of plasma were conducted in this experimental reactor in 2015.
Currently, we are installing the passive diverter and other intrachamber elements. In order to begin the second phase of operation in the summer of 2017, with 20-fold increase in power and pulse extension to 1 minute, the installation will reach its operational parameters in 2020, when it will be possible to launch plasma with a duration of up to 30 minutes and energy parameters of up to 600 megajoules.
The name Stellarator originates from the Latin word stella, which stands for star. This is because the temperature reached inside this reactor is comparable to the temperature of the sun's core. The design of the first Stellarator was created and engineered by American physicist Lyman Spitzer in 1951. This reactor employs the same principle as the tokamak, the invention of Soviet scientists. It is the same closed magnetic trap for plasma confinement. The difference is that the magnetic field in the Stellarator is created by external electromagnets. Due to its configuration, a Stellarator is considered a very reliable and stable installation.
Unlike tokamak, which still operates in the impulse mode due to constantly happening plasma disruptions, Stellarator is a stationary machine due to its nature. That is, if the Stellarator configuration is implemented, it can work in virtually stationary mode, without disruptions.
Wendelstein 7X is installed in the Max Planck Institute of Plasma Physics in the small German town of Greifswald. As of now, it is the biggest and the most modern Stellarator in the world. The diameter of its central part is 17.5 yards. This is not taken into account all the peripheral systems surrounding the reactor. The total weight of the installation is 725 tons. But even if this huge machine will help scientists advance in the understanding of the processes occurring in plasma, Wendelstein 7X is not destined to become a running thermonuclear reactor. However weird this may seem, it is too small for that.
Unfortunately, in order to achieve the reactor parameters, it is necessary to enlarge the plant 4 times. But while engineers can do that, physicists aren't sure whether they are able to predict all plasma parameters as necessary. Therefore, now there is a discussion going on about building an intermediate Stellarator installation, which will be 3 times higher than our machine, and ensure actual nuclear possesses on it.
Moreover, a Stellarator has its disadvantages. Its operation hasn't been studied properly. Its design turned out to be so complex that scientists weren't even able to build it for a long time. The existing level of technology prevented them from doing it. There is no surprise that the study of Stellarators was abandoned, while the operation of tokamaks didn't stop for a second.
Tokamak is just winning the competition. No one excludes the possibility of a breakthrough in stellarators. But as of now, tokamak is the obvious and undisputed winner of the race.
This is why the tokamak was selected as the basis for construction of the biggest experimental thermonuclear reactor in the history of mankind. It was named ITER, Latin for way, and is now being built literally by the whole world. This is because ITER is the greatest international project. 35 countries of the world participate in its creation. By the way, the idea to unite efforts of different states in an attempt to tame thermonuclear fusion belongs to Russian scientist Yevgeny Velikhov.
Generally speaking, around 1975, it became clear that a single country is hardly capable of it, and that solving this problem wouldn't be expedient for a single country. Therefore, in November 1975, if I'm not mistaken, we offered the Americans and Europeans to work together for the first time.
Various platforms were suggested for the accommodation of the giant reactor in Canada, Japan, and Spain, but in the end, it was decided to start the construction of the century. That's what scientists call it, in the south of France, in Cadarache. The construction of ITER began in 2007 and will continue up to 2022.
Well, there were various discussions, but in the end, it was decided to do it in Europe. In this sense, France has a great nuclear potential. In fact, France has the highest number of nuclear stations in the world. It receives almost 80% from them. The culture and the level of French nuclear power industry and Avera are great, high and obvious, and the nuclear science is well developed. As of now, this is the largest research installation in the world. It cost about 5 times more than the famous Ioner accumulator, the Large Hadron Collider. Mankind hasn't built anything like this before.
So what will the biggest experimental thermonuclear reactor in the world look like? According to calculations, it will weigh as much as 3 Eiffel Towers, 23,000 tons. The diameter of ITER will reach 22 yards and its height about 66 yards. The volume of the plasma that scientists are planning to produce in this grandiose plant is estimated as 1,010 cubic yards, which is 10 times more than in the currently largest tokamak jet. The thermonuclear reaction itself in the bowels of this giant will occur at incredible temperatures, 270 million degrees Fahrenheit.
It is now supposed that the first plasma will be generated at ITER in 2025. In 2025, its full-scale operation will begin. That is, with all heating sources and with the deuterium-tritium mixture, the thermonuclear fuel.
In order to confine such a colossal volume of plasma, the magnetic field in the tokamak has to be very large. At ITER, it will be approximately 200 times larger than the magnetic field of the Earth. These values will be achieved through the use of superconductors, several hundred tons of superconductors.
Normally, superconductivity is used to create large magnetic fields because superconductors ensure greater density of the current, and the losses are eliminated as a result. Accordingly, you can create compact magnetic systems that don't consume as much energy as the corresponding copper electrical magnets would consume, for example.
A superconductor is an extremely sophisticated cable product based on niobium titanium and niobium tin alloys. This cable is literally wound on the inner walls of the tokamak to create a powerful magnetic field.
This is a piece of cable for the toroidal magnet of the ITER tokamak. This piece of cable, which is only a yard long, weighs about 33 pounds. It consists of approximately 1,100 niobium tin wires, and it carries a current in the field of 12 T, a current of 70 kiloamperes. What are its main features? It contains many wires twisted into subcables. There is a cooling channel in the middle and a shell on the outside. This is a steel shell, the so-called conduit. You can see the approximate winding diameter by the bent shape of this piece.
Whatever innovative technologies and colossal resources are used for the construction of ITER, this reactor will become just the first step into the thermonuclear future. It is mostly created to study the behavior of unruly plasma at extremely high nuclear temperatures. And only if the heating and confinement tests are successful, the scientists will begin the construction of the first demonstration reactor. It is not expected to happen until 2030.
Such installation is the so-called demo generation. It shall demonstrate to the whole world that all the technological complex of thermonuclear reactor up to the pickup of energy, of electrical energy, can be realized and implemented. How long will a demo discharge last? It's hard to say at the moment, but we're already speaking of weeks, of course. It is not 1,000 seconds, as it is in ITER. It has to last for weeks. After that, the first experimental station needs to be built.
However, no one can predict how it will turn out in reality, and this is not just because there is a whole string of serious problems in the field of thermonuclear fusion. Many scientists believe that mankind won't need thermonuclear power industry in this century at all. But why?
We have the nuclear power industry that occupies a large place. At the same time, we have to understand that with extinction, so to say, of hydrocarbon power industry, whether it will occur in 50 years or in 10 years, we will have no alternative but nuclear power industry. This is because it is provided with fuel, intellectual, engineering, machine and technological resources. It is developed to the point where we easily build stations and make them safe, and so on.
The operation of each nuclear reactor is designed for 80 to 100 years. The problem is that the fuel for the operation of the reactors is the rare isotope, uranium-235, and its reserves are hardly sufficient to provide mankind with energy for the next few centuries. Scientists believe the upcoming crisis of the nuclear power industry can be avoided with the help of thermonuclear fusion. However strange it seems, the thermonuclear reaction is what allows us to generate more available fuel, uranium-233, producing it from thorium, a heavy, low radioactive metal. The natural reserves of this chemical element are virtually unlimited. Large amounts of thorium are contained in the granite layers of the Earth's crust. The full cycle of production of uranium-233 to the point of production of the nuclear energy will be ensured by the so-called hybrid reactor. According to scientists, it will combine two installations at once, a nuclear reactor and a tokamak.
What do we have in thermonuclear fusion? First of all, a huge number of quick neutrons with mega electrovolt energy is emitted from this donut, from toroid. The energy is about mega electrovolt. The number of these neutrons is really huge, and this is, in fact, the only thing that ensures this fusion. In a regular nuclear plant, a regular station, there are a few neutrons, and we resort to multiple tricks to make them. Therefore, what can we do? First, imagine that you have a tokamak that emits neutrons. You somehow manage to create a regular reactor that generates electrical energy around this tokamak. For example, a liquid salt one, and the number of neutrons will increase greatly. It will be a hybrid reactor, and its efficiency will be improved greatly.
The advantage of this technology consists in the fact that our current knowledge of thermonuclear fusion will be absolutely sufficient to launch a hybrid reactor successfully. This means that the construction can be started in the near future.
From my point of view, the relatively close urgent step is not the thermonuclear power industry, which has been spoken about a lot recently, but hybrid power industry. Moreover, it is relatively pure from the environmental point of view. There are no shards, since the operation principle is different. This is my answer.
According to many researchers, hybrid reactors will help mankind avoid the energy crisis. Even if the reserves of coal, gas, and oil will run out faster than expected, we will be able to provide ourselves with warmth and light. And scientists believe that the dream of building thermonuclear power stations and finding an inexhaustible source of energy will inevitably come true. The only question is, who will live to see it? Us, our children, or just our grandchildren?